Welcome. I'm Dean Groff, head of Danfoss Field Delivered Services for North America, and I'm here with one of our CO2 experts, Mr. Austin Wheeler. Today, we want to talk to you about CO2 adaptive liquid management, the use of ejector technology, and improving your return on investments for all CO2 systems. Next. When we began the request to adopt CO2 systems in North America, there were challenges. First, costs were high, and in hotter climates, the systems were less efficient. This made making the investment just a little bit hard to swallow. As we went along, first costs started coming down, and we introduced things like parallel compression and multi-ejectors, which improved the ROI numbers in warmer climates. Then, Danfoss introduced gas and liquid multi-ejectors a few years ago. With this technology, Danfoss has been able to significantly improve the ROI numbers for CO2 installations across all climates. With gas and liquid multi-ejectors, you can now use the same architecture across all climates at the same time, reducing your energy usage. Next. Now we're starting to see the technology grow. It's gained a solid foothold in Northern and Southern Europe and is expanding into other global regions. Ejectors are not new. They've been in use in water systems for a long time and have also been used in refrigeration in the past. They give you the ability to recover lost energy during expansion and as much as 20% of the compressor energy. Danfoss would like to see CO2 refrigeration systems greatly expand here in North America, and we truly believe that CO2 adaptive liquid management technologies can allow this to happen, while at the same time improving your return on investments. Next. Before I hand the presentation to Austin, who will give you a technical side of ejectors, I'd like to provide you with some links to Danfoss tools that will help you on your CO2 journey. Here, you'll find links to Danfoss refrigeration applications, information about our AllSense solutions, and the Danfoss Cool Selector 2 program. Now, I'll turn it over to Austin.
Thank you, Dean. My name is Austin Wheeler, project engineer with Danfoss. So as the regulatory climate has begun to shift focus to low GWP refrigerants, natural refrigerant options have begun to take a foothold in the discussion. CO2 is one of these natural refrigerants that's been long considered and has been used for some time as a refrigerant for over a century. But now, as we have passed the sunset of the chlorinated refrigerant phase out, Danfoss has begun to pioneer the use of CO2 as a viable natural refrigerant option some 20 years ago. And during the course of what we call the CO2 evolution, the transcritical CO2 booster design offers a simple, scalable design for all types of system footprints. But one of the drawbacks of the CO2 transcritical system is that they're not as efficient, typically in warmer climates, as compared to other HFC refrigerants. But as Danfoss continues to drive the CO2 evolution, parallel compression technology had offered the ability to make some efficiency gains to design in warmer climates. But now Danfoss has presented the multi-ejector solution, which Danfoss, we continue to drive the innovation by making CO2 transcritical systems energy efficient in all climates. But there's been a lot of discussions of ejectors and how does ejectors work. And quite simply, an ejector is just a means for us to harness the available energy that is already in a CO2 system. You can think of it a lot like a chemical sprayer that many have, where you hook up a garden hose, the sprayer mixes the chemicals and the waters together, and it sprays the mixture. The ejector is simply just a mixing device, which has three separate connections. It has the gas cooler inlet connection, the medium temp suction connection, inlet connection from the medium temp compressors, and then the outlet connection that goes to the receiver and the flash tank. And what's happening is, as the CO2 gas leaves the gas cooler and enters the ejector, it begins to pick up speed, and as it's picking up speed, it draws, or as we say, lifts the CO2 mass flow from the medium temp compressor group. It mixes in the mixing unit, and then it leaves together out of the diffuser into the receiver flash tank at whatever pressure the receiver flash tank is operating under. And by doing this, we're able to reduce the amount of overall compressor capacity that's required improving the system COP, and giving us a means of a simple serviceable solution by reducing the overall energy usage of the system. But what is the Danfoss multi-ejector? Basically, it's a series of ejectors that are arranged in a single block, 4 to 6 ejectors for the high pressure and low pressure ejector, 1 to 2 for the liquid ejector. The Danfoss AKPC 782A operates the ejector in a binary fashion to give it maximum control stability. Also, the ejector can be fully serviced in the field with Danfoss service kits and O-rings without having to physically remove the ejector block from the system. Also, there is a built-in inline strainer that can be serviced and cleaned very simply without having to remove the ejector physically from the piping. This offers a means of servicing the ejector in the field whenever it has to be serviced with minimal downtime and ease. Next, we like to talk a little bit about the multi-ejector solution. And really, the multi-ejector solution is actually 4 separate solutions for all different types of system types. First, we have the high pressure ejector, which incorporates parallel compression or is an add-on to the parallel compression design. And what's happening here is that we're just utilizing the available energy during the warmer time of the year to be able to lift a portion of the medium temp mass flow from the medium temp evaporators and then use the parallel compressors to compress that at a higher suction pressure. This gives us a higher COP and is an advantage using the high pressure ejector in medium and large systems, particularly in warmer climates. Next, we have the low pressure ejector, which is based on a similar concept as the high pressure ejector, but it does not require parallel compression. And this offers a first cost advantage, especially when we want to incorporate ejector technology with either convenience store or small store formats. Third, we have the liquid ejector, which works in concert with Danfoss's award-winning Calm solution, otherwise known as CO2 adaptive liquid management. It can be used as a standalone solution, or can also be combined with the high pressure multi-ejector solution for even further energy savings. The liquid ejector and Calm solution works very well in both cooler and warmer ambient and climates. Lastly, we have the combi ejector, which incorporates the technology from both the high pressure ejector and the liquid ejector, but it offers it in a single ejector block for better scalability for medium-sized systems. This also adds an advantage by extending and increasing the number of operating hours of the ejector, further enhancing energy savings. So what we'd like to do next is briefly discuss in some detail the workings behind each multi-ejector solution. We'd like to compare the operation in both colder and warmer ambients and demonstrate what type of energy reduction, energy savings can be realized. First, the high pressure multi-ejector solution in cold ambient conditions. In cold ambients, or when it's cold outside, the high pressure multi-ejector the system will operate like a basic booster system. There's not enough flash gas when it's cold outside in the receiver flash tank to be able to run the compressors. So simply the parallel compressors are going to be off, and then the ejector is just going to act as a high pressure valve, maintaining optimal pressure in the gas cooler. During the warmer ambients, there's going to be enough flash gas in the receiver to run the parallel compressors. Also, because there's going to be a higher pressure in the gas cooler, there's going to be enough motive pressure difference across the ejector for the ejector to lift a portion of the medium temp evaporator mass flow through the ejector, through the flash tank, and to be compressed by the parallel compressors. And by doing so, we maximize the efficiency and maximize the COP of the system by reducing the number of compressors that need to run, and by doing so, we increase the energy savings. A while back, not too long ago, Danfoss did an energy analysis comparing the multi-ejector solution to the operation of a standard CO2 booster system. In this analysis, we looked at 6 US cities, based on their climatic data, also incorporated the algorithms found in our AKPC 782 pack controller, also considering different load profiles and also the ratio between LT and MT loads. With considering all these, one could realize up to 14% energy reduction using the high pressure multi-ejector solution. Again, these savings that can be realized will depend on the specific climatic region in which the high pressure ejector system is installed. Next, we like to talk a little bit about the low pressure ejector multi-solution during cold ambient conditions. So as we said earlier, with the low pressure ejector, it operates similar to the high pressure ejector design, except it does not require parallel compression. During the colder times of the year, the low pressure ejector is going to operate the system just like a standard booster system. It's going to act as a high pressure valve, maintaining the optimal pressure in the gas cooler. And with the low pressure ejector solution, we incorporated a check valve between the medium temp evaporator group and the medium temp compressor group. And in cold operation, all of the flow from the medium temp evaporators will flow through this check valve to the medium temp compressors. However, during the warmer months of the year, there's going to be enough motive pressure differential across the ejector to where the low pressure ejector will be able to lift all of the medium temp mass flow through the ejector, through the flash tank, but compressing that flow with the medium temp compressors at a higher suction pressure. By doing this, the overall system COP is improved at a reduced energy cost. This check valve that I just mentioned, what it will do is ensure that there is the correct pressure differential between the medium temp evaporators and the medium temp compressors to ensure proper operation. As with the high pressure ejector, Danfoss, we also did an energy analysis looking at the low pressure ejector compared to a standard booster system. Again, we factored in the algorithms from our AKPC 782A pack controller and also considered the LT-MT load ratio. With factoring these variables, an annual energy reduction up to 10% could be realized with the low pressure ejector multi-ejector solution, depending on the climatic region in which the system is installed. Next, we'd like to talk about our liquid ejector CALM solution. So CALM stands for CO2 Adaptive Liquid Management. And what we're doing with this solution is not just necessarily a liquid ejector, but incorporating our Danfoss pack controllers, our system managers, and case controllers to give us this holistic solution. And the advantage of the liquid ejector is that it can be used as a standalone solution or combined with the high pressure ejector, but its operating range will allow it to optimize the system in both the cooler and warmer parts of the year. To speak a little bit of how the liquid ejector and CALM solution works, the central control or the central component behind the CALM solution is our AKPC 782A pack controller. And we also have our liquid ejector, which is typically installed in parallel with a high pressure valve. And so the pack controller is going to monitor the system, and when the optimal conditions for the liquid ejector exist, through communicating through our system manager 800A, it will actually change and tell our case controllers, the medium temp case controllers, to change their superheat algorithm from a standard superheat algorithm to what we call ALC mode, otherwise known as adaptive liquid control. And by changing this superheat reference, we're now maximizing the internal surface area of the evaporator. And by doing so, we're able to now, through the System Manager 800A, the pack controller can actually raise the suction pressure set point of the system. And by doing this, we reduce compressor capacity, improve the system COP, and that gives us an energy savings. Also with the system, we have a suction accumulator that's installed in line between the medium temp evaporator group and the medium temp compressors. And in the event that any liquid refrigerant will pass through and accumulate in the suction accumulator. The liquid ejector will be able to suck that liquid through the ejector back into the receiver, and thereby protecting our medium temp compressor group. In addition, if the liquid rises too high in the suction accumulator, there'll be a level switch, and therefore the 782A pack controller will be able to disable ALC mode and return the case controllers back to normal operation. So by this, we're offering a safety aspect as well as improving the overall efficiency of the system, giving us that energy savings with a very simple solution. So looking at the liquid ejector compared to a standard CO2 booster system with our 6 US cities, one can see an energy reduction of up to 12% depending on the climatic conditions. But again, the liquid ejector works very well in both cooler and warmer ambient conditions. This solution can also be combined with a high pressure ejector solution, which we're going to talk a little bit more next. Our fourth solution is what we call the Combi Block HP LE multi-ejector solution. The Combi Block, we're combining both the high pressure and liquid ejector solutions in a single block to give us a enhanced scalability. This is a very good solution for both medium and larger footprints, and it even enhances the energy savings by extending the number of operating hours in which the ejector can operate, even more improving the COP of the system and giving us even greater energy savings. This can also be realized even more so when we incorporate the combi ejector solution with heat reclaim. In looking at our energy analysis with the Combi Block compared to a standard booster system based on our 6 US cities, one can expect an annual energy reduction of up to 25% with our Combi Block solution. Again, this is going to depend on the climatic region in which the solution is deployed, and will also depend on the low temp, medium temp load relationship. Again, combining the solution with heat reclaim will even give us further energy savings. And as Dean will mention here shortly, this is why we want to partner with end users, OEMs, and other stakeholders to increase the installed base and validate these savings with real world data. So how to select the right multi-ejector solution? First off, we want to consider the design ambient conditions in which this system or a multi-ejector system could be deployed. Typically, when design ambient conditions are regularly below 65 degrees, a standard CO2 transcritical system will typically outperform other refrigerants. So that may not necessarily mean that the multi-ejector will give us the energy savings when we're seeing design conditions below 65-degree ambience. But historically, CO2 system efficiency has been a challenge in warmer climates, and that's where a multi-ejector solution is going to give us an advantage. And typically, the warmer the climate is, where we can increase the running or operating hours of the ejector, that's going to give us further energy savings with this solution. The second variable is determining and defining what type of store footprint one has. We've kind of categorized this roughly into perhaps convenience stores, a smaller store footprint, a supermarket, and then perhaps a hypermarket or a very large retailer. And by considering these variables, we can look at each individual multi-ejector solution. And again, with high pressure ejector, that works very well with warmer ambient conditions using parallel compression for medium to large size systems. Low pressure ejector gives us the same benefits or similar benefits as the high pressure ejector without requiring parallel compression, which could be a first cost benefit for convenience store or small store formats. Liquid ejectors can be combined with both small and large systems in both warm and cold ambience. And then the combi ejector combines both the high pressure ejector solution with our liquid ejector calm solution for both warm and cold climates for medium and large size systems. Danfoss also offers the Cool Selector 2 software, which can help even further pick the specific ejector for your system. And again, your Danfoss application engineer can also help even further assist in sizing the right ejector for your system. And Dean, I'll hand it back to you.
Thank you, Austin. You go to the next slide, sir. As we close out our presentation, we want to leave you with some links to the Danfoss products that can address different types of CO2 systems. Now we've got this split out into 4 different sections, starting here with our CO2 mini pack solutions. Next. This is followed by our transcritical booster solutions shown here. Then you'll find our transcritical booster solutions with parallel compression. And then finally, the last slide here is our multi-ejector solutions. Next. So we've provided some information on the technology along with a lot of resources, which is all good. However, as Austin said earlier, beyond providing this information about ejector technologies, we would encourage any retailer to consider partnering with Danfoss on your next CO2 transcritical system. Let us help you and prove that the ejector technology can save you money. If you're interested in a partnership, please reach out to Peter D., Sales Director for Food Retail at Danfoss, and let's get the ball rolling. On behalf of Danfoss, Austin and I want to thank you for your time.